Graphing our inverse trig functions. We saw the basic ones, but what happens if we start playing around with it? Dilating it and what have you. Have to draw 5 inverse sine x on 3. I guess the key thing really is just to work out the domain and range. Now we know our inverse sine function would normally, for the domain, go in between -1 and 1. But that's when it's inverse sine x. So what we're really saying here is, well, x on 3 is going in between -1 and 1. Therefore, our one will now go in between -3 and 3. Just multiply by 3. And we can do a similar thing with the range. So remember, really, this is y over 5. And so we say, well, yes, our regular one goes between -pi on 2 and pi on 2. So this one, y on 5, will go in between that. Therefore, my range, -5 pi on 2 to 5 pi on 2. Now when I draw it up, essentially I can draw exactly the same graph as I had before. I just change the numbers. There it is, the exact same graph. Now, unless I have to draw 2 on the same one, well, that might cause a problem. What I could do is just draw it, put the numbers in, there's the graph. This one's a little bit more interesting, I suppose. Inverse tan of the square root of 3 minus x squared. Now, our domain normally for the inverse tan curve is all real x. But we've got this added restriction here because of the square root sign. I can't just substitute anything that I like. So it's the old, well, hang on, I've got to find square root of positive numbers. 3 minus x squared has got to be greater than or equal to 0. Therefore, x is in between minus root 3 and root 3. Right, the range. When we have a restricted domain, that's going to affect our range. So what do we investigate? Well, let's have a look at the endpoint. X equals the square root of 3. If I was to substitute that in, I get the inverse tan of 0, which is 0. The other endpoint, well, makes sense. We're squaring the x, we get the same answer, 0. Let's have a look what's happening in the centre. When x equals 0, we get pi on 3. So there's our range. We know we're going to go between 0 and pi on 3. Let's draw it up. It actually ends up looking like that. Absolutely nothing like a regular inverse tan graph. What about the inverse sine of the sine of x? It would be tempting just to draw y equals x. The inverse sine and the sine cancel out. Probably got something to do with it. Now, the domain. Normally, we say inverse sine function goes in between -1 and 1. So in this one, sine x has to go in between -1 and 1. And we have to substitute into that function. Well, sine x always goes in between -1 and 1. But it doesn't matter what we substitute in. So all real x, we'll always get an answer for this one, because we'll substitute into the sine function, we'll get something that we can find the inverse sine of. The range, well, because I'm substituting in and I'll get the complete domain of a regular inverse sine function, this one will stay minus pi on 2 to pi on 2. There is no restrictions on the domain. What does it look like? Okay, let's mark off those boundary values. If normally we have the radians on the y-axis for an inverse sine trig, well, because I do know it's based on y equals x, and because I know the range is going between minus pi on 2 and pi on 2, it makes sense to label radians on the x-axis as well. There's y equals x. I know it's got to have something to do with that, but I'll stop it once I get to pi on 2 and minus pi on 2, because I know I can't go any higher. Well, what does it do for the rest of the curve? I could substitute some values in and find, well, what about pi? That's a nice easy one to substitute in. If we were to substitute in, the sine of pi is 0. The inverse sine of 0 is 0. And I could pick other points, and what we actually end up with is this zigzag that goes along the x-axis. Sort of like a sine curve, it is winding along the x-axis, but we've got straight lines instead of curves. What about the other way around? The sine of the inverse sine of x, again, you'd think it's got something to do with y equals x. But this time, the domain is only going to be between -1 and 1. Because the first thing we have to do is substitute into the inverse sine of x. And I can only do that if x is in between -1 and 1. So that becomes the domain of this sine function. The range, I've now got a restricted domain. Let's see what happens. When x equals 1, we get the sine of the inverse sine of 1, which is sine of pi on 2, which is 1. When it's -1, I get -1. In the middle, when it's 0, I get 0. Again, not huge surprising here, because we think of y equals x, kind of makes sense. So let's draw our picture. There we go, mark off the ones and the minus ones. Again, we've got the line y equals x, but it just stops. It doesn't keep going. So that's the difference between the inverse sine of sine x and the sine of the inverse sine of x. That shall do us. 17C.